Study magnetic fields, BiotSavart Law, series on electromagnetic field theory, lecture number 2.11. BiotSavart Law gives an expression for magnetic field intensity. It is known conductors carrying steady currents or direct currents. They are surrounded by magnetic fields or steady magnetic fields. These fields are associated with certain field intensity. That intensity is given by BiotSavart Law analytically. Let us move further to explore the world of BiotSavart Law. What is BiotSavart Law? It describes steady magnetic field, static magnetic field or DC magnetic field created by a steady current or DC direct current. It gives field intensity dependence on source current distribution. H is the symbol for magnetic field intensity as or like E representing electric field intensity. This is considered to be one of the basic laws of steady magnetic fields. Magnetic field intensity, as already mentioned, the symbol is H, capital H. It is a vector quantity, therefore it is indicated by boldface letter. Units are amperes per meter. Electric field intensity is units are volts per meter. Magnetic field intensity units are amperes per meter. This is similar. Magnetic field intensity has lot of similarity with electric field intensity, but in one aspect, critical aspect, it differs from electric field intensity. Magnetic field intensity is not associated with any physical meaning, whereas electric field intensity has a meaning. It is force experienced by unit positive charge. Similar meaning you don't find as far as magnetic field intensity is concerned. Magnetic field intensity is independent of medium. This is another difference between electric field intensity and magnetic field intensity. Here you don't find medium dependent constant. There epsilon is there, but here mu, which describes medium characteristics, which represents medium properties, mu is absent. An expression for this can be found in BiotSavart. For H, expression is given by BiotSavart. What is magnetic field? Magnetic field is the region surrounding a current carrying conductor. So an electric current creates magnetic field. Source of magnetic field is current, flow of charge, electric current. A Danish physicist, Hans Christian Ørsted, discovered it in 1820. This magnetic field was first time it was discovered by Ørsted in 1820, when he noticed a compass needle of next to a current carrying wire turned so that needle was normal to the wire. The wire is there, it is carrying some current. He found the needle turning normal to the wire. It indicates presence of field, some field, magnetic field. It is magnetic compass, therefore magnetic field exists here. These observations were able to give great insights into relation that exists between electricity and magnetism. So Ørsted did some pioneering work. His contribution is tremendous to give certain understanding regarding the nature of magnetic field. After Ørsted's discovery, French scientists Baptiste Biot and Félix Savart together found a relation. It is called BiotSavart law for magnetic field intensity at a point in space in the vicinity of current carrying conductor. So first Ørsted, then the work it was continued by Biot and Savart to find an expression for field intensity in magnetic fields. Now we go to the actual statement of BiotSavart law. The magnetic field intensity, DH, differential field intensity, at an arbitrary field point due to a differential current element IDL. See, suppose there is a conductor, it is carrying current. Let us say I is the current. Here you please consider a small length, differential length for this conductor. Okay. The product, differential length, product current, or current with the differential length. This product is called differential current element. So the differential current element creates certain amount of field. That field here is indicated by DH. That DH is proportional to product of the current by magnitude of differential length and sine of the angle between the filament and the line connecting the differential element to the field. Inversely proportional to R square, R being the distance between current element and field point P. Directed perpendicular to both the differential current element and the distance distance vector joining the differential element with the field point P. The proportionality constant is 1 by 4 pi in MKS system. So basically it involves 3 points proportional to product of current, magnitude of differential length and sine of the angle, inversely proportional to distance square, perpendicular to both direct differential element and distance vector. First point, second point, third point. If you notice, lot of similarity between these 3 points and the points which we encountered in Coulomb's law. There also direction is given, distance relation is given, and also dependence upon charges. Here current element given. Mathematically, the field intensity dH due to current element ideal is, see, he gave field intensity due to current element in word form, in a statement form. It can be put in mathematical form also. dH is 1 by 4 pi proportionality constant ideal. This is current, this is differential length cross R cap by R square. Notice this is proportionality constant. Out of the 3 points, R square is second point and IDL cross R cap. This particular expression, it represents both the first and last points. These 2 points are denoted by numerator. Middle point is denoted by R square. Of course, this is proportionality factor. What is the first point? First point says magnitude wise it is proportional to current, differential length and the angle between differential length and vector joining source point with field point, sine theta or sine alpha. Okay. And what is this last point? It is about the direction. Those 2 points, they are combined, they can be combined and they are combined here in the numerator, IDL cross R cap. The first and third points are combined in the numerator, the cross product. The field intensity H due to the entire current becomes natural. So what is this dH? He considered a line current like this. Some current is flowing. He considered differential length dl. He called this product, IDL product, as differential current element. Okay. He considered an arbitrary point P. At this point, what is? Of course, in the region surrounding this current distribution, there exists field intensity. There exists field. Field is associated with field intensity. We considered an arbitrary point P in the field. And what is field intensity here? First, he is giving expression for field intensity, differential field intensity or field intensity due to this differential current. Due to this fellow, what is field intensity? That thing he is calling it as dH due to this. Now I want field intensity due to the entire current carrying conductor. Then I have to perform integration over the source. So performing integration over the source gives I by 4 pi dl cross R cap by R square. For your information, what is R? This is source point, field point. R is always. Now, 3 different types of current distributions are available. They are line current or filamentary current, surface current and volume current. Line current is one or filamentary current is one which is flowing in a thin wire, very thin wire, and surface current is one which is flowing in the form of a thin sheet, whereas volume current is one which is flowing in a thick conductor having certain cross-sectional area and all that. Right. Using equivalence among various current elements, BiotSavart law can be extended to surface and volume currents. In the previous slide, we considered H, field intensity due to line current, filamentary current. Now, expression for surface current, expression for volume current, we want to see. The expression for field intensity due to line current is shown here in A. It gives you a better understanding. H equal to 1 by 4 pi integral I R prime cross R cap by R square dl prime. Here R prime, capital R, all those things are obvious. They are having their meanings, obvious meanings. Now, there is an equivalence between current elements. IDL is equal to KDA is equal to J d tau. Note, DL means differential length, DA means differential area, d tau means differential volume. I is current in amperes, K is surface current density, amperes per meter, whereas J is volume current density, it is amperes per meter square. IDL equal to KDA, KDA equal to J d tau. Equivalence is there among these 3 quantities. So now I can extend this expression to other current distributions also using this equivalence. When you extend it to surface current, you will be getting K cross R cap by R square. Here it becomes J cross cap by R square. We have used prime, dl prime, da prime, d tau prime. Reason is prime indicates that integration is to be performed over source distribution. When integration is over the field point or around field point, then prime is not used. Therefore, magnetic field intensity H is for line currents H R equal to 1 by 4 pi IR prime R cross R cap by R square dl prime. For surface current, I is replaced by K and dl prime is replaced by dA prime. For volume currents, I is replaced by J and surface currents, current density is differential surface area is replaced by differential volume. So, basic law, Biot-Savart law, when coupled with that equivalence, all these are resulting. Here, R prime are position vectors of source and field points respectively. Notice here also field intensity is inversely proportional to distance square. Field intensity is proportional to current. It is similar to expressions for electric field intensity. One more important thing here is Biot-Savart law is able to give direction of the field intensity at a point, but it appears somewhat complex. There is a rule, it is called Maxwell's rule. Maxwell-Corkscrew rule. Using this rule, one can find the direction of the field very easily. Another name for this is right-hand thumb rule. So Maxwell's-Corkscrew rule or right-hand thumb rule. What is this rule? It gives you a simple way, easy way by which one can find the direction of the magnetic field. To find direction of field, a simple technique was devised by Maxwell. It is illustrated here. To determine the direction of field, what you have to do is hold the current carrying conductor in right hand, that the thumb points towards direction of current. Suppose, see, here is conductor, current is upwards. Now hold it such that your thumb is pointing towards direction of the current. There is only one way you can hold it, with your thumb along direction of the current. Now wrap the fingers around the conductor. The direction in which fingers point gives the direction of magnetic. This is the Maxwell's corkscrew rule. In A, current is upwards, your thumb is upwards, so your points, your fingers are, you can wrap your fingers only in anti-clockwise direction. Not possible to wrap in clockwise. When the current is downwards, when thumb is downwards, you can wrap your fingers only here also. Of course, you can wrap them in only one way. Okay. So that gives you the direction. Here is shown the direction. Opposite. Direction of the field is opposite. Here it is leftwards. Here leftwards. Here it is rightwards. Right. Another thing which is required to be introduced is magnetic flux density. This is similar to D in electrostatic fields or electric fields. Magnetic flux density symbol is B. By definition, it is mu H. The proportionality constant mu is called permeability, a term first coined by Heaviside. As already mentioned in the previous videos, Heaviside is a great scientist, as great as his contributions are as tremendous, as significant as those of Maxwell. It is a property of the medium. Mu is property of the medium. It is similar to your epsilon. The units of flux density are Tesla, or T named after Nikola Tesla, a famous Serbian American inventor. It is also measured in Gauss. Tesla, Gauss. Gauss is small unit, Tesla is big unit. It is related to Tesla through 1T is equal to 10K Gauss. Earth's magnetic field is half Gauss. Magnetic flux is also there. B is flux density, whereas phi is magnetic flux. These two are related. Magnetic flux is integral B dot dA. The units of flux are Webers. It is named after Weber, a German physicist who with Carl Gauss invented the first EM telegraph. Also, he is credited for the usage of letter C for the first time to denote speed of light. As the flux density is flux per unit area, the units Tesla or Webers can be related. Tesla and Webers can be related as Tesla E equal to Webers per square meter or Webers per WB by per meter square. So this is what I want to share. I can share regarding Biot-Savart law for the time being. Thank you.